Thank you for joining us. Appreciate your participation. This week we have a great talk by Jeffrey Weekley from UC Santa Cruz, and he'll talk about Kubernetes, which is becoming more and more relevant in HPC. So with that, I'll welcome Jeffrey and turn it over to you to do your presentation.
Thanks, Mary. And I'm quite pleased to be here, even though it's Friday afternoon. And my dogs are wondering why we're not out for a walk, but we're going to get through this. So let me go ahead and share my screen, and I'll start with the slides. Let's see here. Here we go. So today we're going to talk about interactive HPC using containers on Nautilus. And I'm sort of mashing up some terms here, and we'll get to what all of those mean. But we're going to talk about the Pacific Research Platform and a very important tool running on that called Nautilus, Kubernetes, which you may have heard of, and then in general, containerized software. And I will not be monitoring chat, but if someone from the teaching team could do that and let me know if there are any questions, I'd appreciate it.
Yeah, no problem, Jeffrey. Also, Igor is here, so he'll be very helpful.
Oh,
yeah, great.
So this is our agenda today. I'm gonna introduce myself, and then we'll go into a little bit of background, and we'll talk about containers in Kubernetes and how you would access Nautilus, as well as software tools, controlling the cluster, data, and some other things like Jupyter Notebook. And we'll have some time for Q&A at the end. So this is about me. I am the Director of Research IT at UC Santa Cruz. I'm also the local program manager for the NSF funding program that's building Nautilus in its second phase. And as such, I'm in charge of engagement and outreach. So this fits quite nicely into our program activities, and I'll be happy to report to the PI that we're doing this. I'm also a PhD student in my third year, working part-time in computational media with Baskin Engineering at UC Santa Cruz. And computational media, if you don't know, is work that exists at the intersection of computer science, human-computer interaction, design, and social systems. My particular area of emphasis is improving science communication, and in particular around ocean conservation. Before that, I was Director of Research Computing and Cyber Infrastructure at UC Merced for about 4.5 years. And I was actually over in New Zealand when I took that job. I had been working over in New Zealand for about 2 years as the Science Engagement Officer for the National Research Network. And the majority of my career was spent as a research scientist for the US Navy at the Naval Postgraduate School in Monterey, California. And there were a few odd jobs before that. So I was sitting in New Zealand, minding my own business, and all of a sudden I hear this news that Larry Smarr and Tom DeFonte and a few others are building this thing called the Pacific Research Platform. And I had known about science DMZs, and working at the National Research Network down there, we sort of built this high-speed science network there. And so this concept of a research platform built on top of that was the natural evolution. It's grown to be more than 50 institutions. And really what it allows is a very high-end, high-speed, end-to-end data transfer, data collaboration capability built on the very capable Scenic and Pacific Northwest Gigapop fiber optic networks. Now, if you've ever heard Larry give a talk, and he gave one last fall at SC about the evolution of this kind of thing, he always mentions that, yeah, the photonic, the optical networks that connect all these institutions up are really high speed. But as soon as they hit the campus network, and as soon as they hit a particular computer, all that high speed is for naught, because either the network on the campus or the computer itself can't ingest or serve data at those speeds. So in its beginning, the Pacific Research Platform was really about trying to engineer out the complexity and make sure that someone sitting in their lab in Santa Cruz is able to connect to somebody sitting in their lab and at UC San Diego at 10, 40, or even 100 gigabits or faster speed, and have the machines keep up. And so rather than just building it and hoping people would show up, they identified some use cases and worked with those use cases to build this system. And it's been very successful. It's now in its 7th year. It's gathered over $7 million in NSF funding, which is a very successful program. And it's really led to the rise of some data-intensive science collaborations. And one of the things that it enabled was the Nautilus, this next generation cluster. Before I talk about Nautilus, though, I'm going to share with you just a quick movie about what the PRP is doing and how it's advancing the science applications. So I'm going to play that from my desktop rather from my slides. So you should see that now.
The data revolution is transforming fields as diverse as astronomy, archaeology, and earth sciences. This work depends on and is stored as trillions of data points. Today's data-intensive scientists need to quickly and easily store, analyze, and move these large data sets between collaborator labs, supercomputer centers, scientific instruments, and data repositories. Just as the high-speed, end-to-end, no-stop lights interstate highway system transformed the American economy and social mobility in the 20th century, the big data cyber infrastructure of the National Science Foundation-funded Pacific Research Platform promises to transform scientific advancement in the 21st century. The PRP's superhighways, with network speeds from 100 to 1,000 times faster than commodity internet, are provided by regional optical networks such as CNIC in California and its partner networks, nationally and internationally. PRP's on-ramps to these optical fibers are rack-mounted PCs, each containing powerful multi-core CPUs, up to 8 gaming graphics processing units, and large amounts of storage. Many of these PRP endpoints are drop-shipped to remote campuses, but in California, our UC San Diego technical team used the old-fashioned road trip to visit and install rack-mounted big data endpoints at campuses from UC Santa Cruz to UC Santa Barbara to Stanford University to UC Merced and back down to UC Irvine and UC Riverside. Internationally, these PRP endpoints span from Korea to the Netherlands. In the United States, there are over 180 of these big data PCs located and operational on 25 partner campuses, 10 of which are minority-serving institutions. California is home to the largest number of PRP campuses. Pacific Research Platform users place their application in software containers, and then the PRP uses Google's open source Kubernetes to orchestrate the movement of these containers across the distributed PRP system or into commercial clouds. Because of PRP's aggressive containerization and high-speed networking strategy, to the user, the PRP's over 7,000 CPU cores, 500 GPUs, and 4,000 terabyte storage appear to be in the same room, while being interconnected by CNIC, the Quilt, and Internet 2. The PRP is uniquely designed for working with multi-campus science teams from a wide range of application disciplines. Let's look into 3 examples of the over 400 projects actively using the PRP. Neutrino observatory data analysis, networked virtual reality systems, and prediction of wildfire spreading. A major use of the PRP is data analysis of the massive digital output of observatories. For instance, the National Science Foundation South Pole Ice Cube Neutrino Observatory is designed to detect astrophysical neutrinos. Spheres containing digital photosensors are attached to vertical strings, which are lowered into the boreholes, where they are frozen in ultra-transparent Antarctic ice. When a neutrino that has traveled across intergalactic space collides with an ice atom's nucleus, it creates a charged particle producing a cascade of blue light, which is detected by thousands of ice cube photosensors. The data analysis of when each of the photosensors detects the blue light provides information on the direction in space that the neutrino came from. Graphics processing units compute millions of photons propagating through the ice. The neutrino data is sent to the University of Wisconsin-Madison IceCube team, who then runs high-throughput computing on the Open Science Grid, OSG, a global distributed system of over 140 computer clusters. The OSG can in turn request usage of the PRP's GPUs. By mid-2020, IceCube data analysis was using nearly half of PRP's 500 GPUs for months at a time. Moving to the second example, modern archaeology is able to capture 3D digital movies on location and convert them into virtual realities. The PRP enables 3D high-resolution images of the ruins of Luxor in Egypt captured by UCSD PRP team to be shown on the UC Merced Wave by pulling the data from UCSD over the PRP to Merced. The same Luxor dataset can be viewed on two other virtual reality systems, Qualcomm Institute's Sun Cave on the UC San Diego campus, or the Citrus Cave Kiosk, inspired by the cave kiosk in the Hearst Museum of Anthropology on the UC Berkeley campus. These virtual reality systems are powered by the PRP PCs, which provide nearly 100 of PRP's 500 GPUs, available in standby mode to support the PRP applications such as IceCube data analysis and machine learning. A final example is this public service PRP application developed in response to destructive wildfires becoming the new normal in California. With support from the National Science Foundation over 20 years, the High Performance Wireless Research and Education Network and its partners built out meteorological stations and hundreds of cameras across Southern California. Those sensors constantly stream data into PRP's big data PCs, which are connected by optical fiber networks to the San Diego Supercomputer Center. There, these second-to-second data updates are integrated with detailed topography and fuel loads by the NSF-funded Wi-Fi cyber infrastructure to better equip emergency responders to model and predict fire behavior using real-time data sources and machine learning models.
The director of Cal IT2, Larry Smar, and the chief data science officer at San Diego Supercomputer, Ilkay Altuntaş, put those pieces together to how you can make the technology and the hardware and the simulation and data science integrated into a platform that can be seamlessly intuitive to firefighters and the public.
When you think about a location and time that the fire starts, there is a number of data that you can bring together. If you could bring together all the data, you can actually enable fast decision support using models, data science, fire science. So that's what Wi-Fi achieved.
Field resources initially are very limited. We'll run a model, the initial model, here from the center, and with the capability of the program, we can put it in a shared file. I could take a picture of the screen, whatever means possible to be able to get it to those initial decision makers that are out in the field, because they're making decisions on what's a realistic containment area for this fire, if at all possible. Where are we going to be able to stop it?
The Pacific Research Platform has convened annual workshops in 2017, 2018, and 2019. Attended by hundreds, including the leaders of the major national networking organizations ESNet, Internet2, and the Quilt. We held workshops for minority-serving institutions and NSF under-resourced EPSCoR states and invited their leadership speakers to increase inclusion and diversity in the PRP communities. In addition, the PRP team has attended major technology conferences such as the annual Supercomputing and Scenic meetings. The Science Engagement team has also created smaller on-campus workshops to engage new members. Providing technical training and expanding our growing PRP community continues to be a central focus of the PRP grant, with both in-depth technology courses, weekly technology video meetings, and detailed documentation on how to get started in the PRP website. To accelerate the rate of scientific discovery, researchers must get the data they need, where they need it, and when they need it. Join the community, collaborate at the speed of light, and unlock tomorrow's discoveries. To get involved, visit pacificresearchplatform.org.
Okay, so you are now all involved because you're going to learn how to use that stuff. All right, so I'm going to go ahead and start sharing my slides again. So you heard about how the Pacific Research Platform was formed. You heard a little bit about the applications that are running on Nautilus. And now we're really going to take a deep dive into especially Nautilus. So Nautilus is a highly distributed but centrally managed community cyber infrastructure. It's an on-demand, real-time accessible cluster with more than 500 GPUs and 7,000 CPU cores. And I'm going to talk a little bit later about how Nautilus differs from traditional HPC. But the key thing to remember here is that it's real-time accessible. There are currently about 187 nodes that provide service from all 10 UC campuses and many partner institutions. And we have researchers from over 30 campuses across the world who use it. The reason why we were able to build Nautilus is because the National Science Foundation had already invested a lot, over $20 million in campus networks. And it turns out that campuses don't charge us for power and networking and cooling. And so we can actually provide services cheaper than you might get by owning your own equipment or by going to a commercial cloud. So
Jeffrey?
Yes.
Sorry to interrupt. I don't think you're sharing your slides, actually.
Oh, well, we need to fix that. So share screen, basic, slides. Okay, so does everyone see that now?
I see everything. You haven't done.
Great.
Yes, there you go.
Okay,
It
so
looks good.
this is just, just what I said. It will be there on the record. And so the key thing here is down at the bottom. Unlike traditional HPC, Nautilus is interactive. And I'll explain what I mean by that. So now we're going to talk a little bit about containers and orchestration schemes and how this thing all runs. So first of all, what is a software container? Well, containerization is the idea that you package up all your software code with just the operating system libraries and dependencies required to run the code to create a single lightweight executable. It's different than, let's say, running software on your laptop. And it's certainly different than something like a virtual machine. It's really just the code and enough libraries to run the code and nothing more. And it presumes that all of those other things that you need to run a program in the kernel are available by the system. So on the left here, we have containerized applications. And we see app A, B, C, D, E, F running in a Docker environment. Now, we don't happen to run Docker on Nautilus. We run Kubernetes, but it's the same idea. The host operating system provides a lot of the support. And of course, the infrastructure is the bare metal, the graphics card, the server, the hard drive. In a virtual machine, everything gets virtualized. So it's an abstraction of the physical hardware that turns one server into many servers. And it allows you to do things that you can't really do in a container. And it contains a full copy of the operating system, all of the applications, the necessary binaries and libraries. And typically, these hypervisor things that orchestrate all that are commercial software that you have to pay a license fee for. Kubernetes is actually open source. It was originally a project from Google. It is now pretty much free for everyone to use. So unlike a virtual machine, that's a rather heavyweight piece of code. A container of software is rather lightweight. you in this series have been learning about traditional HPC, and I looked at the schedule, and you're learning how to use Slurm and, you know, write batch job scripts and do all these other things. And you know that once you write your script and you submit your job to the cluster, you pretty much, you know, leave it alone and it just runs. And if you're lucky and if you're good, it'll run successfully, and at the end, it'll spit out your results. Kubernetes, on the other hand, is interactive. And while it is still a workload manager, it really focuses on running these very lightweight containers and not much else. It says, oh, you have requested these resources in your container. Here is a piece of infrastructure that can run it. And once it's running on that infrastructure, Kubernetes really has very little to say about how long it lasts and what you do with it. You can do more sophisticated scheduling with Kubernetes, but it's pretty atypical. So, like I said, it's an open source container orchestration system, and a lot of people conflate, you know, the software container and the orchestration and the command and control tools, and just say, oh, it's Kubernetes. We're going to get a little bit more verbose today, and so you're going to learn a lot of vocabulary. So we're going to start with some of the key concepts of Kubernetes, which is the orchestration software. So it has a control plane that manages the workload, handles the internode communications, keeps knowledge of the cluster state. That's this middle layer that you see called Docker here. A node is a physical machine where the containers are deployed. Each node has to have a container runtime. On Nautilus, it happens to be container D, but container D and Docker and Kubernetes are all pretty much interchangeable. Namespaces, which is something that you'll hear quite often, is a way for Kubernetes to partition cluster resources across multiple or many users in an exclusive way. So when you access the Nautilus cluster, you not only access it as a user, you access it as a member of a group which has a namespace. And namespaces allow you access to resources in the cluster. Sometimes you have priority access, sometimes not. For instance, when we ran the visualization software at Merced in a namespace called the Wave, it had priority over namespaces. So when I needed to run a visualization on the wall, all those nice Ice Cube people running Ice Cube simulations got kicked off and they went somewhere else. Pods is another word that you're going to hear very often, and those are the basic scheduling unit of Kubernetes. A pod consists of one or more containers running inside of it, and each pod gets a unique IP address, which is very important, so that microservices or applications can access the pod without contention. However, pod IP addresses and everything else associated with the pod are ephemeral. So when you shut down your pod, everything that existed in that pod goes away. And that's a really key thing to remember. Services are a set of pods working together. Let's say you might have one pod actually doing calculations for you, and you have another pod that is running a web browser that is showing a visualization for you. And those two things can work together quite nicely. Those services and pods working together are often called deployments. So for Nautilus, these are the nodes. So on the top, we have the GPU node, and you can see that we have space for 1, 2, 3, 4 on the top and 1, 2, 3, 4 on the bottom, graphics cards with a small array of disks. Below in the lower right, that's a storage array, and we'll talk about why that's important. And those two are the basic building blocks of the Nautilus cluster. The standard network connection for the GPU node is 10 gigabits per second, and the standard connection for the storage node is dual 100 gigabit connection. And the reason why the storage nodes have such robust network capability is it's conceivable that many users could be trying to access their stored data at once. So in Nautilus, a namespace are really groups of users working together. So if you went to the Nautilus webpage, which you eventually will do, you will see this page when you bring up namespace overview. So in this example, Avis Citizen Science from UC Santa Cruz is the namespace group name. The admin, so if you wanted to get access to this namespace, you would contact Fahim. And the professor or the PI is Alex Peng. And everyone who runs jobs on Nautilus has to be part of one of these groups. Okay, like we said before, pods are the smallest, most basic deployable object in Kubernetes. A pod represents a single instance of a process running in your cluster. Sometimes they contain one or more containers, and a Docker container is a way for you to package up your code and deploy it on the cluster. Pods also contain shared networking and storage resources for the containers. So for the network, they're automatically assigned a unique IP address. And the pod containers share the same network namespace, including IP address and network ports. So communication between pods in the same namespace is very, very easy. And this is one of the reasons why containerized software has really taken off. It's because it takes all of those things that are kind of hard in dealing with traditional HPC and makes them fairly easy. So containers in a pod can communicate with each other inside the pod just on localhost. It's as if they're running on their own computer. Storage. Now, a storage pod specifies a set of shared storage volumes that can be shared amongst the containers. So you can request a storage pod that is permanent, and you can connect it to your non-permanent network pod in a way that lets you access the data at very high speed. And we'll talk about that as well. So that's the basics of the sort of the vocabulary and the and what a pod is and all of that stuff. Maybe I'll pause if there are any questions from the chat. Have we had any questions?
No, I don't believe so.
Okay. So we'll
nothing technical.
Okay, we'll continue on. All right. So now that we have that basic information about, the difference between HPC and Kubernetes and basic vocabulary of Kubernetes, now we're going to actually get into, if you were a researcher, how would you go ahead and get access to Nautilus? So there are 3 levels of access to the Nautilus GPU cluster. There's the guest, and that's, what you get when you initially log in. You're automatically a guest. Once you're validated, you become a user. And then if you need to run your own namespace, you can request to become an administrator or an admin. So if you go to nautilus.optiputer.net, you will find this login page. And this is the PRP Kubernetes portal. And if you hit the login button, you will be taken to a CI login screen where you declare your affiliation. So if you're a student at UC San Diego, you will go search for UC San Diego, Santa Cruz, so on and so forth, and that will take you to your campus single sign-on, your central authentication tool. And for me, it looks like this. So I just put in my regular credentials from my university and am logged in. You'll see a very similar page to this, and you'll be logged in as a guest. Guests have credentials, but no privileges. And this is because you can imagine that if we gave somebody automatic access to something as powerful and diverse as the Nautilus cluster, we might end up finding ourselves with lots of Bitcoin miners or other nefarious activities. So even though most of the system is automated, you will actually have to go and get permission to use the cluster. And that is done in the Matrix chat. We'll talk about that in a minute. So once you have, before you can get elevated to a user or an admin, you've got to get a configuration. So this configuration, it tells your computer and the cluster how to communicate with each other. It's a configuration file that goes into your local directory. You download it, and then you create a folder inside of your local directory called .kube. And the dot before a Unix file system name means hide this folder to a file system browser. So you're not going to see it if you're just using your regular tools on your computer. So for me, I download the configuration. I use the command line make directory, this .kube.cube. I move that config into that directory, and then I verify that it's there. Once I have that, so this is what that config file looks like. And it's a certificate that tells the Nautilus cluster who I am and that it's okay for me to connect. So it contains public and private keys, and it allows for you to automatically connect to the cluster without having to sign in. So once you have your user account as guest, you have your credentials as guest, and you've got your configuration loaded, then you can go to the next level and become a user. So guests can navigate to the Matrix chat in the Nautilus support channel and say, hey, I am Jeffrey Weekley. I'm at UC Santa Cruz, and I'm going to do research in machine learning. I would like to be added to my professor's namespace. And in my particular case, that is the creative coding namespace. The helpful people in the chat would go ahead and elevate you from a guest to a user, and then you would be able to join that namespace. So if you wanted to have your own namespace, and you were, either you had your own research project, or you didn't have a PI, but you wanted to explore the system and use it, you would then ask to be created into an admin. And once you're an admin, you can actually make your own namespace. So this list here, the Creative Coding, Forbes Lab, Gandalf, JLab, NLP, my namespace, all of these are namespaces that I actually am an admin for. So if you wanted to join, let's say, the Creative Coding namespace, you would tag me in Matrix, and I would allow you to have access to that namespace. This is what the matrix chat looks like. You can either do it in a web browser, or you can get the Element standalone tool. All of that is available at that URL. And you can see there's a little bit of dialogue here about what can and can't be done as a user or an admin. So pretty much all of the support for Nautilus is actually done through Matrix Chat. And there's a lot of reasons for that, but it's mainly because the Nautilus is a community infrastructure. And so rather than having a single source of authority that has all the answers, everyone is expected to participate in the chat and help their peers and their near peers when they have questions. And this allows us to scale our support for Nautilus users much larger than we otherwise could support. So you have your username. You have been elevated to a user. You've joined a namespace, and now you have to figure out how to use this thing. So now we're going to talk about the software tools that you need to actually use the cluster. So you've gotten access, and now we're going to talk about what you can do with that access. So I like to make the analogy of baking cookies when I talk about Nautilus. So the ingredients you choose are your code, and you can adjust those to your needs or your taste. You might be making a chocolate chip cookie, or you might be making a peanut butter cookie, or you might be making a snickerdoodle, whatever. The code you choose are the ingredients. The mixer, you've got to mix these ingredients together, are your development tools like Docker. And we're going to talk about what that looks like in a minute. The YAML file is your recipe. This is you telling the Nautilus cluster how you want to put these cookies together. Coupe Control is controls the oven, all the settings, and Nautilus, of course, is your oven, and it helps you make your delicious cookies. So in order for you to gather up your ingredients, your software, you're going to need to be able to either use someone else's software, create your own, and then eventually deploy it up to the cluster. So Docker or other containerization software is used to create images or software containers. It's common practice to develop inside of Docker running on your local machine. So you can make changes to your code while you're actually developing it. That's called DevOps. And once it seems to be running the way that you think it should run, then you're ready to go ahead and deploy it. And we'll talk about how you do that in a minute. But unless you're making a pretty unusual cookie, it's likely that there are already pre-built images for most everything that you would want to do already existing in a place like Docker Hub. It contains thousands of pre-built images. So if you wanted to build a web server and run Apache and serve web pages, there's a container for that. There's no need for you to do any kind of development at all. You basically just pull down the container, modify it to your needs, put it up in your own repo, and then use that copy when you go to deploy it to Nautilus. So once you know what software you're going to use, whether it's stuff that you've built yourself or stuff that you've borrowed from others, you will use a YAML file as the instructions or the recipe for your deployment. And ultimately, Coupe Control or CUB-CTL is the tool that you would use to launch your deployments. So let's look at Docker. So we know that Kubernetes is the orchestration framework for deploying this containerized software, but it's actually naive about the software. So in order for you to develop services, you'll need to create your own software to deploy. And as I said, most people simply reuse software by referencing pre-built Docker images, and there are thousands of them there. And you can use your own, you can make your own using Docker on your local computer. So if you want to reuse the code, you would go browse available containers at hub.docker.com. If you want to develop your own, which you probably will to some degree, you would go to docs.docker.com, get started. This is the basic workflow for that process. So you're down in the lower left, you're the software engineer, you're the operations engineer. And if you look at the top, you'll see Docker Hub. You go and you find what it is that you want to do up here in this public image repository. You get a copy, you modify it, and hopefully you're using some kind of version control. Once you have it working, you test it on your local machine. And once it seems to pass all the tests, you push that up to your own private image repository, your GitLab. Now, it may be that you didn't need to do any kind of modification at all. You just ran it in Docker on your local machine. It worked. You push it up to your private repo. And then you have to write your YAML file. And we'll look at that in a minute. And this tells the Kubernetes cluster, this orchestrator, how you want to run this code. So the code plus your configuration in your YAML file pushed up to Nautilus gets you to run it. And of course, there's a bunch of downstream stuff here, you know, monitoring and results and all that other stuff. And I'm not really addressing storage, which we will here in a second. But that's the basic workflow. So let's imagine that you have access, you're in a namespace, you found the exact container that you wanted to run. Let's say it's PyTorch for doing machine learning training. You found the container, it works for you on your local machine, and now you're ready to scale up to a really powerful platform with lots and lots of graphics cards. You're gonna need to write a YAML file. So code is what you will run, YAML and Coupe Control is how you will run it. So what is YAML? And it started out as kind of a tongue-in-cheek thing, yet another markup language. It sort of emerged at the time when XML was becoming a thing and everyone was writing markup languages. And they really didn't, you know, they wanted to give it a name, but they didn't really care. So they just said yet another markup language. Now YAML is a nested acronym and it stands for YAML ain't markup language. So the humor continues. Anyway, it's a human readable data serialization language. It's commonly used now for configurations. It's similar to XML, but with fewer syntactical conventions. It has Python style indentation to reflect hierarchy and order of operations. It's pretty loosey-goosey when it comes to typing. It can encode strings, integers, floats, and even arrays. And most Nautilus users don't make their own YAML files. They find one in an example and they modify it. And ultimately, it's used to request resources, deploy services, and your code in containers, of course. So this is what a simple YAML file looks like. So we have the API version 1. The kind is a pod pretty standard stuff. The metadata and the name is test-pod. And you're going to need to remember that, because when you go to monitor the resources and how things are going, you're going to need to remember the name. So it's, in this case, all this YAML file is doing is instancing CentOS 7 on the cluster. It's going to use 100 megs of memory. It's going to use 100 M of CPU. And the command, once you have CentOS running, is sh with the flag C, echo, I'm a new pod, and then go to sleep forever. So why in the world would you write a pod like this? Well, you would write a pod like this and use this to familiarize yourself with the interface, and not much more. But everything that you send up to the cluster is going to be sent there by a YAML file. So now we've done all that stuff. We know that we can send we know we can instance a simple pod up in the cluster. We've got our name, we've got our namespace. How do we actually control the cluster? Well, that's done with this command on your command line called Coupe Control. So before you can do any of that, any of the tutorial, you're going to need to install this tool on your laptop. And you can do that from that URL there. So this particular tool is used to deploy applications, inspect and manage cluster resources, and view logs. It's basically your way to interact with the cluster. And here's the structure of this command. So it always starts with CUB-ECTL. You'll get very used to typing that. The next portion is the command. What do you want to do? And they're limited to these operations. Create generates new resources. So if we go back up to our YAML file here, if we wanted to create a pod with these characteristics, we would type Coupe Control create, and then give it the YAML file. Describe retrieves details about a resource or resource group. So you can use this to figure out what is available to you. Get fetches cluster data from various sources. Delete removes resources as directed. And that's very important because pods themselves will persist unless you delete them. And if you leave them up too long, you're going to get a note. And apply pushes changes based on your configuration file. Type specifies the category of resources you're targeting. Name is case sensitive, and it specifies the name of the resource. If you leave name blank, it'll apply things universally and maybe to everything in your namespace. And flags are the modifiers that you use to give special options or requests. I don't typically use that flag, but sometimes you never know. So you have the ability to basically instance your own version of a pod, which is a little mini computer. But what are you going to do with it? What if you want to, let's say, do a machine learning workflow, and you're going to be training a machine learning algorithm? You need to have data. So, and if you remember, I said that pods are ephemeral. They don't persist. Once you shut them down or they crash, they go away. But there's actually a way to have persistent data in Nautilus. It's a different thing than managing computing instances. And your storage is provisioned through this persistent volume claim. And Nautilus comes in distinct classes and regions. So in this table, you'll see that we have different storage classes and different regions. And it's very important to remember that if your data are going to be on the West Coast, you should also do your computation on the West Coast, and vice versa. So most of the time, you're probably just going to be using this one right here. Let me see if I can find my cursor. It's this default one right here. And you can also see that's a very large allocation. And so there should be plenty of space there for you. I don't know why I can't see my cursor. Let me exit out and see. Oh, this is awkward. I'm sorry. I am not able to see my cursor, so I can't navigate. This whole thing seems to be frozen. Okay, hold on.
I did see you drawing something there for a moment,
Yeah,
Jeffrey, then it went away.
Okay, there we. Okay. Let's see if I can get back. Oh boy.
You can stop and restart if you want to.
I think that's what we should do.
Good.
Okay. Let me go ahead and stop share. We'll start again.
I see your cursor now.
I know, but as soon as I actually start the show, it goes away. Very awkward. Okay, well, let's just power on.
Are you using dual windows?
No, I just have an iMac.
Okay.
Okay, so if you needed to put data up in Nautilus, or when you need to put data up in Nautilus, you will use a persistent volume claim. And it's a special kind of a service, and it persists. There are other types of storage in Nautilus. First, there's the local storage. Most nodes in the cluster have local NVMe drives, which provide fast I/O, faster than the file systems. These can be used for workloads that require very intensive I/O operations. So you might specify that you want to use local storage. And in that case, your pod would actually fetch the data from your persistent volume claim, load it into local storage, and then operate it on it from there. If you weren't operating on local storage, it would likely load into memory. And that would work fine for most things, unless you were dealing with very large files or rather very intensive I/O operations, lots of read-write. There's also the ability to store your data in Nextcloud, and you can get a Nextcloud instance running on Nautilus. It's similar to other file sharing systems like Dropbox or Google Drive, and it can be used to get data into the cluster. You can also use it to write your results, share data, and so on. So Nextcloud is a service that runs natively on Nautilus. And if you wanted to use Nextcloud as kind of a shared drive, you would just pop into chat and ask to be provisioned with a Nextcloud account. Seaweed.fs is a high-performance distributed file system. It's optimized for working with huge numbers of files and also huge files. So many files and many large files. It's different than Ceph. And I would say that if you need to use Seaweed.fs, you're probably not a beginning learner anymore. Good for you. And all you need to do is pop into the chat and explain your use case, and the community will give you some guidance on how you might use this distributed file system. So Seaweed.fs is in some ways very much like the distributed file system and distributed memory that you might get with an HPC instance. So it's starting to span that gap. SyncThing is a tool to synchronize file collections. So, if you've ever used, rsync as a command line tool, it's very similar. It creates a mesh between all the devices, and it works well for large file collections. Let's say if you were, collaborating with somebody and they were changing a file somewhere and you were changing a file somewhere, and you wanted to make sure that you had all of your files in sync, SyncThing would be the right tool to use. So practically, for many users, the easiest way to get your data up into your pod is to use Coupe Control, and it has a copy function. So Coupe Control -n my namespace copy where your local file is up to the name of your pod and where you want it to go in there in the temp directory or wherever. Now you can imagine that this would work really well for small data sets, things that would transfer easily over, let's say, your home network or the network at school or Starbucks or wherever you happen to be. It's not really a good idea to try to transfer a large data set. So I would say anything, over maybe the 5 or 10 gigabyte, the size of a 4K movie download, you might not want to do that. Especially if you're tethered to your phone, you'd crash your data plan pretty quickly. The other thing to keep in mind here is also that transferring your data up in this way means that the data exists only in the pod. And what do we know about pods? They go away. So once the pod is gone, so is the data. Now there's this concept of S3. Now I'm not going to get into S3 too much, but it's a way to manage large data sets, and it's the most scalable way. And you can follow the slides, the link in the slides for more information on S3. Once your data are up inside your pod, you can manipulate it from inside using your pod, using standard Linux tools. So if you examine the Coupe Control, there's actually a way to log into the pod itself. And once you're in there, you can treat it like any other command line. So here are a few other considerations to keep in mind when you're using the Nautilus cluster or any sort of Kubernetes orchestrated cluster. Many users break their workflow into services, and some of those services even into microservices. A microservice is an architectural design for building a distributed application. So instead of running everything in a single pod, you actually run multiple pods that are connected to each other, and each pod actually performs a different service. So you might have your computation happening in one service. You might have your data fetch happening in another service. You might have your monitoring or even visualization or output in yet another service. So in this way, if you imagine your computation is continuing, and let's say you're tweaking your output, your visualization, let's say you're using a Python to build charts, you can, instead of stopping everything, you can actually let the computation continue, and you just fiddle with the pod that contains your output graphs. Since they're loosely coupled, as you start and stop the visualization pod or the graphing pod, the computation pod is unaffected. And that's called DevOps. That's the way a lot of people do large scale deployments now. You can scale it. Let's say you were running your computation and it started to slow down. You could just instance another pod for more computation while your graphing and your data fetching pods all just kept doing what they do. And this is how the internet runs now, actually. When you open up a web browser and go to Google and you type in the search bar, you're not actually going to a server. You're actually creating your own instance of a Google search engine. And that way, you know, even if all of us together all at once did a Google search, we wouldn't crash the Google servers. So that's really one of the foundational motivations for Kubernetes, is that you have these loosely coupled microservices that can run independent of each other and can be updated or scaled, shut down, started up without having to shut the whole machine down. So, like I said, the Nautilus cluster running on PRP is a way for you to run your own applications, do your own research in a container or a suite of containers called a deployment. But there are also tools that are running all the time there. And these are some of the tools. So you may have encountered Jupyter before. The Nautilus runs a Jupyter hub for West Coast and for East Coast. And those are always running. That's just a service that runs inside of Nautilus. WebODM is a drone map image stitching. So if you, let's say, wanted to create a 3D landscape and you've got a bunch of drone images, you don't need to build that service inside of Nautilus, it's already running. And the reason why we have WebODM running as a service is because there are a lot of researchers, especially in the digital humanities, archaeologists and whatnot, who actually do this all the time. They just need this all the time. And it was much easier for the engineers to stand this up as a service that exists all the time than ask all of these researchers to learn how to use the cluster in this way, you know, on their own. AppWrite is a backend server for web, mobile, others. So if you have an application that needs to run web, you can use AppWrite and you get all that functionality without having to build your own. And then there's, you know, things like Etherpad for writing notebooks, GitLab, which is a code repository, Jitsi for video conferencing, which I don't use. Nextcloud, we talked about, you know, it's kind of a Google Drive or a box running on Nautilus. And it's nice because it's already there. If you write technical papers, you may have encountered LaTeX. Overleaf is running on Nautilus. And Overleaf is a really nice interface that makes it easy to write these technical documents. And then for the engineers who build and maintain the cluster, we have a couple of monitoring tools. Traceroute, which gives you, wide area network connections, and PerfSonar, which is a test and monitoring software that tests the network connection speeds, if there are any drop packets, network reliability, and things like that. So many people first encounter, or many people start using Nautilus by using the Jupyter Hub, Jupyter Lab instance of Nautilus. So I thought I would take a minute or two and talk about that service. So it's one of those things that even as a user, you're going to need to request access because it's not given automatically, but it's given rather permissively. So if you're a user, you can access Jupyter. You just need to request. And it's typically for people who want to do, machine learning development. So automatically in Nautilus, you're assigned, you have the choice of choosing a graphics card. And, there's some older cards here, like a 1080 is, a 5 or 6 year old card, but it's fine. There's some really powerful cards like the RTX A100 and the A40s. And I just put in a purchase request for 2 machines that have A6000s. So these are very powerful supercomputer style graphics cards that can do highly precise calculations over very large data sets. The A6000 has, I think, 48 gigabytes of RAM. In addition to having these variety of graphics cards, let me just say, before I move on, let's say you were developing a machine learning algorithm, you could actually use this to test your algorithm against all of these different graphics cards to help you decide which one you wanted to target for scaling up or purchasing your own. So it's a very nice experimental platform. Let's say you were writing a paper about a new machine learning technique, and you could demonstrate that it runs at these different benchmarks. That might be a very nice table to include in your paper. So not only do you have a standard set of a wide variety of the graphics cards, you also have a lot of pre-configured images. So you can run all of these different kinds of stacks. I tend to either run a TensorFlow stack or sometimes just a minimal stack. And all of these are available, so you don't have to then go into your notebook and build the software from scratch, which if you run notebooks at all, you know that's a typical maneuver. You can upload your own IPython notebook. So let's say if you were running something locally, you didn't have a really powerful graphics card, you thought you could use one, you can just upload your Python notebook to your instance of Jupyter running on Nautilus, and it'll just work. Now you're going to probably have to replumb your data, but it really does give you the ability to develop locally and then scale up to Nautilus itself. And another very nice thing about the Jupyter notebooks is that the notebooks actually themselves persist. So even though the pod, the instance running your particular notebook is gone, the system keeps, the hub, Jupyter Hub, keeps track of your notebooks. And the next time you request a Jupyter notebook running on Nautilus, it'll actually be there for you. So none of this business of the pod goes away and everything is lost. So this is what the interface looks like. It should be quite familiar to some of you. And it's a very powerful tool. So this is often where I ask people to start with Jupyter or start with Nautilus. Once you have your code running here, then you can turn it into a container and run it at scale. So putting it all together, here, the software tools and configurations you'll need to get Docker, Coupe Control. You'll need to have that config file in that directory that you just made. You can use Docker locally to build custom containers, or you can use Docker Hub to pull down pre-built software containers. Access to Nautilus is granted at 3 levels. Once you log in and authenticate to your home institution, you'll be a guest. You pop over into Matrix and you request to be elevated to a user to join someone else's namespace. You request to become an admin to create your own namespace. And then you can invite users to join your namespace. Coupe Control is the command line tool that lets you interact with the cluster. Your YAML file that you usually write from an example tells the cluster what you want it to do. Do you want it to create a CentOS instance? Do you want it to allocate some persistent storage? Do you want to have a pod that simply spits out a web page? It's up to you. Deployments are groups of pods and services that make up your workflow. And as we saw in the DevOps model, you can make your deployment in microservices, and you can change things on the fly, which is quite different from traditional HPC. Storage outside of your pod is available through a persistent volume claim or one of the other things like Nextcloud. And as I said, Jupyter Lab is a great place to start exploring. So that's about all I have. And I guess I'll open it up for Q&A. And before we leave, I'm going to take you over to the actual Nautilus website, and we'll poke around a little bit there. So I just want to pause now and give anyone a chance to ask questions on the presentation.
And Jeff, I'll just add in that you and I'll be making a namespace for the training class. And Jeff's paper is uploaded onto the GitHub repository. And once we get the namespace created, we'll post the updated information on the training repository.
Yeah, I don't expect everyone in the audience to fully grasp this. In fact, you know, I put these slides together over the last week or so, and for me, this is a very helpful thing because it's a bit of a jumble. There's a lot of pieces and parts, and it totally seems like a name your own adventure kind of thing, which it sort of is. Hopefully I sort of broke it down into the basics, the things that you'll need. And I'm sure this group is smart enough to be able to figure out how to use this very powerful tool on their own.
Well, I'll kick off the question. If you could go back to the slide before, which was like the putting it all, yeah. So simple, obvious question to you guys who've used it. When I use Coupe Control, that's a Kubernetes command. And by putting in the specific namespace that I'm using, and I understand I can list them, that namespace knows that it's connected to the Nautilus cluster as opposed to some other cluster that supports Kubernetes, and B, it knows that it's like a particular namespace that Mary is going to set up. Is that
so
correct?
almost. So it's that little hidden file up in the .kube directory.
Okay.
Your config file.
The config file, okay.
Is the thing that tells your Coupe Control what cluster to talk to.
What if I want to talk to multiple?
Then you would have to manipulate that configuration file in a way.
Well, it's
Okay.
easier than that. You can pass on the command line
Yes.
the
what-
configuration file you want to use. You
Right.
can have as many as you want. That's just
Excellent.
where the default is.
Yeah,
But
that's what
you
I
can
meant.
definitely point to any other one if you have multiple Kubernetes clusters you talk to.
Okay, okay, that
So
explains
in
it.
my particular case, I have a config 1 and I have a config 2 because sometimes I want to actually talk to Kubernetes running on my local machine.
Yeah.
And sometimes I want to talk to the one running on Nautilus.
Okay, that's the magic I was trying to put together. So that makes a lot of sense that I use the configuration files to set up connections to different Kubernetes hosting machines.
That's
and
right.
then the namespace is basically my allocation, my account and allocation.
Right. So
Okay.
the cluster is going to check, A, do you have, credentials to talk to me? And that's that, big long hash. And then B, are you a member of that namespace? So are you allocated resources under that namespace? So those two things are required for you to actually be able to start a pod.
Okay.
By the way, the configuration you usually get from Nautilus doesn't have a default namespace associated with it. Actually, it is default, which you cannot really use.
Right.
And you will need to explicitly specify which namespace you want to use. However, the config file can really be much bigger than what Nautilus provides. And you could tweak it to insert the default namespace and many other things. But that's a really advanced topic and can get you in hot waters really fast if you don't know what you're doing.
Yeah. Typically, if you're going to be working in the same namespace again, there's actually a little shortcut that you can declare on the command line that lets you know, hey, this is my namespace. This is where I'm going to be. I don't have to declare it, -n my namespace every time. So that's how I sort of tackle that problem, just to save a few keystrokes. But yeah, you can have your own configuration in the config file if you're an advanced user.
Great, thanks. Anybody else have questions? Feel free to ask. There's one here. Is there any cost to having an account or running code on Nautilus?
So that's the beauty. No, there is no cost. Now, I didn't mention it, but if you hear a talk from Tom DeFonte, who is the PI on the continuing grant, Tom is going to talk about potluck computing. Now, for our American students, or maybe even our Canadian or North American students, they understand what a potluck is. A potluck is a group of people who all come together and each person brings something, a dish, to share. You might bring a dessert, and your friend might bring an appetizer, and someone else might bring a main dish, someone might bring a salad, and everybody comes to the table and they put their little dish down, and then you can choose whatever you want from all the available dishes. And Nautilus is like that. Everyone brings a little bit of something. Some people bring a 1080 Ti graphics card. Some people bring an A40. And they put them down, and then the rest of us get to choose from them. So while the program has been very successful and actually gotten millions of dollars in grants, most of the equipment that's in Nautilus was actually provided by people just contributing. And so they have brought their dish, and it's there for everyone to share. So in that way, we don't have to charge people to use this. We can offer it as a service to the community.
That's awesome.
That said, people who are heavy users of Nautilus, will typically buy their own equipment and make it available to the community when they're not using it. So for instance, that big tile display that I showed, the Merced Wave or the UCSD Sun Cave, those things are actually, those graphics cards are most of the time working on Nautilus stuff. But once in a while, someone needs to go in and use that infrastructure. And so the people that were using it before get moved off and their pods go spawn somewhere else, and it's used for the visualization. Same if I were, let's say, to buy a server with a bunch of graphics cards for my lab, and I wanted to have first priority, I would join them to Nautilus, but once I wasn't using them, they would be available for other people. And Kubernetes scheduler would actually, task those machines. So we've had researchers at UCSC campus purchase their own GPU server and then say, okay, this is for my lab to use. And I'm monitoring them and they're being used about 30% of the time. So there's 70% of that machine that could actually contribute to the community. So the other side of that coin is that when I, as a researcher, let's say I am operating on my 8 GPUs and I'm really onto something and I want to scale up to 100 GPUs, if I'm part of Nautilus, I can actually scale to that level. If I'm on my own, I can't. So that's the idea of this community computing, potluck computing. You bring a little something to the table, and once you are at the table, you can have as much as you want. It's an all-you-can-eat buffet. Does that make sense?
Yes, we have another question, but I'll just ask very quickly. Do people contribute Raspberry Pi clusters?
Well, we have a standard sort of set of infrastructure for Nautilus. And the reason is because it all needs to be sort of managed by a very small team.
Okay.
So the hardware itself is all pretty standardized.
Okay. All right.
And so in that way, no. But could you run Kubernetes on a Raspberry Pi cluster? Absolutely. And I'm sure many, many people do.
All right, we have some students in our supercomputing club looking for projects, but we can talk later. Maybe they can put up a cluster managed by the club as a node. We have a question here from Amit K. If Nautilus is a community resource, is it like OSG resources that an institution could contribute resources to? You may have answered that.
Yes, it is. And in fact, there is actually a mapping between the Open Science Grid and the Nautilus cluster. If there are processes running in the Open Science Grid that are waiting or that need resources that are specific to the Nautilus cluster, they can actually run on Nautilus. So if you remember the video, in the video, there was this thing about the ice cube researchers down in Antarctica. Let me just remind everybody by pulling up that frame in the video. Those people were actually using the Open Science Grid, but because they were requesting, they had jobs and requesting resources that were particularly well suited to the Nautilus cluster, that workflow all ran on Nautilus. Now, in the second version of Nautilus with the continuing grant, we hope to be able to go the other direction as well. So things that are too big of a scale for Nautilus itself will spill over into the Open Science Grid. And we're still working on that. Isn't that right, Igor?
Oh, yeah, something along the lines. Yeah. One has to keep in mind that the Open Science Grid, let's show my face. The Open Science Grid is essentially a typical batch system, not unlike what you get with Slurm. It just happens to use Condor, and it's not really suitable for HPC because nodes can be spread all over the place and you don't have high-speed networking between nodes. But for single node applications, it's pretty much the same as any HPC system. It's a batch. What Kubernetes brings to the table, like Jeff said, it's networking and storage configuration. And if you need that in Nautilus, you will not be able to get it in Open Science Grid because it's a batch system. So it's much easier to overflow from Open Science Grid into Kubernetes because essentially Kubernetes is richer than a batch system. But anybody that doesn't do anything too fancy in Kubernetes and it's essentially uses Kubernetes as a batch system, yes, it could be overflown back to the Open Science Grid. Like most batch systems, OSG supports containers, so that part is relatively easy.
Do you guys support, or do you plan to support Singularity containers?
Well, Singularity containers, most of them are just really Docker containers. The problem, or the way Singularity is usually used, it's on the HPC systems, is that you have the Singularity container pre-staged in a shared file system.
Mm-hmm.
And right now there is no shared file system that Kubernetes uses. So in theory, it's possible. It's not supported out the box right now, and simply because it's a different model.
Okay, yeah, and I'll point out to the trainees here that on Expanse we support Singularity. We don't have Kubernetes because Expanse is a batch queuing system, which we talked a little bit about a couple of weeks ago. And next week, Marty Candiz will talk about Singularity on Expanse. And then if sometime towards the end of April, we're still finalizing dates, Igor and Jeffrey will be doing a tutorial on Kubernetes. So we'll let you guys know, and it'll be open registration and held virtually. Just putting a plug in down the road for people interested in learning more about this innovative, exciting area. There's a question. Are there any cons to using Nautilus apart from the non-persistent pods?
Well, you know, let me just flip that on its head for a second. The reason why Kubernetes is so popular is because of the lack of persistence. And you can create and destroy and create and destroy and create and destroy these pods at will, and you know, in very rapid succession, and in many instances. So it's very good for provisioning a service rapidly, configuring it dynamically, and managing it dynamically. What it's not really good for is, let's say you wanted to have, in traditional HPC, let's say you were doing a batch, an array job in a batch script, which you take a data set and a set of operands, and you run a job with the first operand on the data set and the second operand and the third operand and so on and so forth. And then you get this big pile of results. In an HPC system, you're sharing that memory, right? It's a very efficient way to do something like that. But in Nautilus, you're not. It's not a shared memory system. So every time you wanted to do one of those operands on that array, you would have to copy that whole array and get it over to the pod. And that's just not an efficient way to do things.
Well, I would disagree here. Sorry, Jeff.
Go ahead.
So Yes, the containers are not persistent, but it doesn't mean that you cannot have a persistent storage. And actually, Jeff mentioned a couple of them, Ceph, CWDFS, where you can persist. It's just not part of the pod. So Kubernetes allows you to provision external storage that will persist. Now, Nautilus is not meant to be HPC system. So the shared file system that we have, like Ceph, it's not the same as you would get at an HPC system. For one, it's not collocated, like Expanse, it's all in one room. Ceph is distributed across California, pretty much. And two, Lustre was optimized for HPC, and Ceph is not. So you could potentially do similar things that you do on the HPC system, storage-wise, on Nautilus, on Kubernetes, put it that way. But that would require Nautilus to be all in one room, and it's not, for all of the reasons that Jeff has explained.
And you can't do shared memory operations once you go past a single node, right?
Well, you can do it on HPC system either. You would need to have MPI or whatever.
Right.
So networking is there. It's not InfiniBand, and nodes will likely be on different in different data centers. So it's just the latency will be high. You can still do everything, just latency will be high because Nautilus is not in a single data center like what people usually expect from HPC. So conceptually, there is nothing to prevent it. It's just Nautilus was not designed to be a low latency system across multiple nodes. So on a single node, as HPC or Kubernetes makes really very difference. But when you need something that runs across multiple nodes, well, Nautilus is just not an HPC, doesn't have HPC class networking because it's distributed. So you cannot beat the speed of light. Latency will be high.
In addition to, you know, some of those latency issues and issues with scaling, there's also just the fact that it's a system that many people contend with. It's contentious. So if you want a popular type of graphics card, you may need to wait. So if you need a dedicated resource that's available to you all the time, you might consider actually paying for it instead of trying to get it for free. For most people who are doing research in machine learning, it's more than adequate. It's amazing. But for large scale production type things, it's not appropriate.
Although you can look at the demonstration done by Frank and Igor et al. A couple of years ago, demonstrating large scale computing using distributed resources. So, but also, you know, the non-persistent part of things is just HPC anyway. You either submit a job to PRP, NRP, or the Slurm scheduler or some other queuing system. And in a sense, that's not very persistent either. So I think it's getting late in the afternoon, and we've had a wonderful presentation from Jeffrey, and I wanted to correct one of the things I said. Marty did talk about Singularity last week, so I'm correcting myself on that one, and reminding everybody that next week we'll talk about interactive computing. I think that I'm on the schedule for that. And notebooks and interactive computing. So I want to thank Jeffrey and Igor for being here and helping us out. If you have more questions, you can contact us or go on the Slack channel, and we'll try to answer questions as best we can. Don't forget that Slack is our resource for helping and answering questions. I'm updating the GitHub repository for this week, and when I get all the the information from Jeffrey, like our namespace, it'll be on that page. And with that, I also wanted to ask you, you talked about potluck computing. Have you heard about the Stone supercomputer? That was a potluck type of computer made back in the, I'll put it in the chat, in the I don't know when it was the late 90s, and they took every extra piece of computer workstation they could find at Oak Ridge, put it together, and their goal was the cheapest cost per flop, as in zero. So zero cost. So anyway, it was an example. I like to refer to that when I'm talking about the early days of parallel computing. So
Well, I think every
interesting little-
cluster I've ever built was a soup kitchen cluster.
Yeah. Yeah. It's kind of, I love the potluck concept. So, okay. So with that, thank you everybody. And thank you, Jeffrey and Igor. You're all free to get up and move about the country and enjoy your weekend. Thank you for coming. I hope you can get online and do some of these experiments, and we'll be in touch.
Bye-bye.
Bye, everybody.
Bye.